All right, in this video, I'm going to go through and I'm going to do some proofs of the more commonly used trigonometric identities. And I'm going to start with our Pythagorean identities. And these hinge off of the equation of the unit circle. And remember, the equation of the unit circle here is x squared plus y squared equals 1. And around our unit circle, we defined all the x values as cosine values. And all of the y values on the unit circle were sine values. And so if I substitute in for x and y for cosine and sine respectively, that's going to give us that cosine squared of theta plus sine squared of theta is equal to 1. So there's our first Pythagorean identity. Now, I can take this Pythagorean identity, cosine squared plus sine squared equals 1. And I'm going to rewrite this identity such that I have tangent in my problem. And I can create tangent if I divide sine, or in this case sine squared, by cosine squared. Now I'm going to divide all the terms by cosine squared. And in doing that, cosine squared divided by itself makes 1. Sine squared divided by cosine squared makes tangent squared. And 1 divided by cosine squared makes secant squared. So there goes a second Pythagorean identity. And I could create one more. So let me start back with cosine squared plus sine squared is equal to 1. And now let's say instead of seeing a tangent squared, I want to see cotangent squared. Well, cotangent squared is created by me taking cosine squared and dividing it by sine squared. So I'm going to divide my entire problem by sine squared. And when I do that, that creates cotangent squared x plus 1 is equal to cosecant squared. So there are our three Pythagorean identities. Cosine squared plus sine squared is 1. 1 plus tangent squared is equal to secant squared. And cotangent squared x plus 1 is equal to cosecant squared. Now, the next one that I want to derive here is the cosine of a difference. And we're going to use this cosine of a difference here to derive some of the other ones that are going to come after it. And what we have here is, you look over here on the left-hand side, is I have a circle here that's at the origin, and I have 2 points that fall on the edge of the circle, A and B. And the coordinates of A are some value of cosine and some value of sine for x and y respectively. And the same thing here for B is that the coordinates are going to be cosine of angle B by sine of angle B. And the angle in between them here is defined as theta. All right, and so what I'm going to do is I'm going to take this circle on the left and I'm going to rotate it into the standard position such that I have the same angle theta. So here's my endpoints of the angle. And theta is still the angle in between, in this case, C and D. Now, what I'm going to do is, because there's the same angle and I just rotated it slightly different, is that I'm going to use my distance formula to set up and find the distance between BA. So the distance from B to A has to equal the distance in between C and D. Now we're going to use our distance formula from algebra here to continue on. So the distance between B and A is going to be equal to the square root of, I'm going to subtract my x's and square them, so it'd be cosine of B minus cosine of A squared, plus the difference in my y squared, which would be sine of B minus sine of A squared, all being square rooted. Well, that's the distance from B to A. Now, the distance from C to D, I'm going to do the same distance formula, but I'm going to use their coordinates. So that's going to be equal to the square root of cosine of theta minus 1 squared plus sine of theta minus 0 squared. And now, so that's right off the distance formula. So distance formula. Now what I'm going to do is I'm going to square both sides. So after I square both sides, I'm going to be left with what is up underneath the radicals. So that's going to leave me with just cosine of B minus cosine of A squared plus sine of B minus sine of A squared. And that's going to equal cosine of theta minus 1 squared plus sine squared theta. So all we did here was we squared both sides. All right, well, from here, now I'm just going to expand all the binomials. So working my way from the left, that's going to be cosine squared B minus 2 cosine B cosine A plus cosine squared A. And then plus sine squared B minus 2 sine B sine A plus sine squared A is equal to, now I work my way to the right, so cosine squared theta minus 2 cosine of theta plus 1 plus sine squared theta. All right, well, looking from here, I see that I can have some Pythagorean identities because I have cosine squared B, sine squared B, cosine squared A, sine squared A over here. And we also have cosine squared theta plus sine squared theta. And if I put those together, so I put together my Pythagorean identities, we're going to have, well, actually, I tell you what, let me write them next to each other so we can see what we have. We'll have cosine squared B plus sine squared B. All right, so that's one of my Pythagorean identities. And then we have plus cosine squared A plus sine squared A. So there's a second one. And then we still over here will have minus 2 cosine B cosine A minus 2 sine B sine A. So that's my left-hand side. My right-hand side, I have a Pythagorean identity, cosine squared theta plus sine squared theta. And then I have, we still have a plus 1 minus 2 cosine of theta. All right, well, our Pythagorean identities say that cosine squared plus sine squared is 1. And we just did that. So we have 1 plus 1 minus 2 cosine of B cosine A minus 2 sine B sine A is equal to 1 plus 1 minus 2 cosine theta. All right, so that's, we applied our Pythagorean identities. All right, and simplify this a little bit. So we have 2 minus 2 cosine B cosine A minus 2 sine B sine A is equal to 2 minus 2 cosine theta. Well, the 2's are going to cancel out here. All right, and then I'm going to divide everything in my problem by 2. And in fact, I'm going to divide everything by a negative 2. And that's going to make cosine of B times cosine of A plus sine of B sine of A equals cosine of theta. So what do we do there? We divided by -2. Now, at the very beginning, and I'll go back up here so we can see it, theta is defined as the difference in the angle of rotations between A and B. And so I'm going to resubstitute in for theta, so that way my whole problem is in terms of A's and B's. So cosine B times cosine A plus sine of B times sine of A is equal to cosine of A minus B. So we resubstitute for theta. And we have our proof here of the identity for cosine of a difference. All right, the next one we're going to derive is cosine of a sum. So we have cosine of A plus B, and I want to know what its identity would be. Well, up to this point, we have defined how to find the cosine of a difference. So we're going to use an algebra technique, and we're going to rewrite the A plus B as A minus negative B, and then we're going to plug that in to our cosine of a difference formula that we just derived there a second ago, which would make cosine of A times cosine of negative B minus sine of A times sine of negative B. Well, to proceed from here, we're going to use even-odd identities. Cosine is an even function. Sine is odd, which means that I could rewrite this as cosine of A, and since cosine's even, that means cosine of negative B is equal to cosine of positive B. And sine, being an odd function, means that sine of negative B is equal to -1 times sine B. And we could simplify this. And so our cosine of a sum identity is cosine A times cosine B plus sine A times sine B. All right, so there's cosine of a sum. We've derived that one. Now let's look at sine of a sum and sine of a difference. All right, so what we're going to do here is we're going to let x, because we're going to let x be equal to A plus B. And to find sine of a sum, we're going to use the cofunction identity here, that sine of x is equal to cosine of pi over 2 minus x. That's a cofunction identity. And so what we have, slide over, is sine of A plus B is going to equal cosine of, and we're going to put in the A plus B, and so that makes pi over 2 minus A minus B. All right, and we have three terms in here, so what we're going to do to proceed to use our identities is we're going to group the pi over 2 minus A and let that be a singular term that in terms of an angle inside of the cosine of a difference. And then we're going to go do a cosine of a difference, which would be cosine of pi over 2 minus A times cosine of B minus sine of pi over 2 minus A times sine of B. So we use the cosine of a difference formula right there. And now we're going to go back and we're going to do cofunction identities here. So cofunction identities. So cosine of pi over 2 minus a, that's going to make sine of a. And then we have cosine of b. And then minus sine of pi over 2 minus a makes cosine of a. And then times sine of b. So there is our sine identity for sine of an angle sum. All right, now let's do sine of a difference. Well, to do this, we're going to use the same algebra trick we did before, and we're going to say that sine of a minus b is equivalent to sine of a plus negative b, since we just derived the formula for sine of a sum. And so we're going to rewrite that right-hand side and say, okay, well, that's going to make sine of a times cosine of negative b minus cosine of a times sine of negative b. And we're going to use our even and odd identities and say, okay, well, I have these negative angles inside of here, so we're doing even odds. Cosine is even, sine is odd, which means that I could rewrite the first term as sine of a times cosine of positive b. And since sine is an odd function, sine of negative b is going to make negative 1 times sine of b, so that's going to turn this into a plus. So plus cosine of a times sine of b. So there's our sine of a difference. Now let's look at some double angle identities. All right, so the first one will be the double angle of sine. And to derive this one, we're just going to use the sine of two angles adding together, and both angles are going to be x. So if I do that, sine of x plus x, using our angle sum formula for sine, was going to make sine of x times cosine of x plus cosine of x times sine of x. And these are like terms here, which means that I have 2 times sine x cosine x. So there is our double angle identity for sine of 2x. Well, let's do the same thing for cosine. So cosine of a double angle identity, we're going to rewrite that cosine of 2x as cosine of x plus x, and we're going to do the angle sum formula for cosine. So that's going to make cosine of x times cosine of x minus sine of x times sine of x. Well, I can square those two terms, and that's going to give me cosine squared x minus sine squared x. So there's a double angle formula for cosine. Now, since I have cosine squared and sine squared in this formula, we actually can rewrite this double angle formula a couple of different ways. And in fact, there's 3 ways to write this one. And so I'm going to take that double angle formula that we just wrote. So we have cosine of 2x is equal to cosine squared x minus sine squared x. And we're going to use our Pythagorean identity here. So the Pythagorean identity, I'll write it over here to the side, is cosine squared x plus sine squared x is equal to 1. Well, if I was going to replace cosine squared, if I subtracted the sine squared to go to the right-hand side, that means cosine squared x is equal to 1 minus sine squared x. And so I'm going to put 1 minus sine squared x in right there, which is going to give me 1 minus sine squared x minus another sine squared x. And I combine my like terms there, and a similar form, or a second form of the cosine of a double angle would be 1 minus 2 sine squared of x. So there goes a second formula for cosine of a double angle. And let's do a third one. So we have cosine of 2x, the very first one we did. We rewrote that as cosine squared x minus sine squared x. And let me write that Pythagorean identity back over here to the side. So cosine squared x plus sine squared x is equal to 1. Well, let's say this time I want everything to have cosine in it. So I want to replace the sine squared. So sine squared of x, according to our Pythagorean identity, is equal to 1 minus cosine squared x. So I'm going to replace sine squared with 1 minus cosine squared. So that's going to make our identity become cosine squared x minus 1 minus cosine squared x. Well, that's going to give us 2 cosine squared x minus 1. So there's a third Pythagorean identity, or not Pythagorean, a third double angle identity for cosine by using our Pythagorean identities. And the last one, in terms of common ones that you encounter when doing proof, are power reducing identities. And these all come from our double angle formulas. And in fact, the double angle formula for cosine. And I'll show you what I mean here. And there's two of them that I'm going to write. So I'm going to split this right in half. All right, so the first one's going to be, let's talk about the double angle formula for cosine of 2x. We have equals 1 minus sine squared x. See, the power reducing identity wants to take a squared term and rewrite it in terms of a non-squared term. So in this case, I have sine squared, 1 minus sine squared x equals cosine of 2x. Actually, there should be a 2 in front of there. It should be 1 minus 2 sine squared x. And so I'm going to start rewriting this to be sine squared equals. So this makes 2 sine squared x equals 1 minus cosine of 2x. And then if I divide my problem by 2, I have sine squared x is equal to 1 minus cosine of 2x divided by 2. There is one of our power reducing identities, and it just comes from the double angle formula for cosine. Now let's do the same thing using the double angle formula for cosine that is in terms of cosine squared. So cosine of 2x is equal to 2 cosine squared x minus 1. Well, I've moved the 1 to the other side. I forgot that 2 again. And then divide by 2. And we're going to have cosine squared x is equal to 1 plus cosine of 2x divided by 2. There is the second power reducing identity, which reduces cosine squared into a cosine with the 1 power.